volts up to, right? So for this type of machine, the HD reactance and XQ reactance are not sensitive. Basically, this HD is greater than XQ. In this concept, today we will try to derive the expression of P for the expression that we derived for P, this expression, okay? This expression for P, right? This was for the non-serial formation because we neglected the serial formation. But gradually we are actually considering the saliency of the generator. That's why we actually in the last class studied about the salient mode machine. And today actually we want to derive the expression of P for salient mode generator. Okay. So for that one, first we have to draw the phasor diagram. Because from the phasor diagram it will be convenient for us to obtain the expression of P for salient mode machine. So actually I think you all know this quantities, right? VT, IA, RA, XD, XQ. I think you should know this quantities by this time, right? So what is the first step for phasor diagram? We have to draw the reference line first, right? What is our reference line? We say that this imaginary bus voltage will be our reference, right? Because we know that here the voltage magnitude is fixed and also the associated angle is assumed as 0 degree. And this is the reference point, so here the associated angle is 0 degree, right? That's why first we will plot this line. This VD, angle 0 degree. The voltage of our image. First we will plot this dot V. Why we draw it at an inclined angle, that will be clear to you, because whenever we will draw the E, the induced EMF of the generator. Okay, we want this E horizontally, so that actually our calculations make sense. That's why we are drawing the VT at some inclined angle, so that our E remains at the horizontal axis. Okay, that is the part. Because this is our reference, we can draw it at any angle. Okay, so this is in our hand. So we are first drawing it here. Okay, so this is 50 angle 0. This is our point. Then the second step, draw the armature current phasor. Okay, we know that the armature current is obviously a phasor quantity. It has both magnitude and the angle. So this is the armature current IA, and what is the angle? Angle is theta. Why? Can you know why the angle is represented by theta? Because here this theta will be the power factor angle, right? We know that in any system the voltage difference between voltage and current is called the power factor angle. So here we have drawn the voltage. Okay, so that is the VT. With respect to this, the angle of the current will be theta. But whether it will be plus theta or minus theta, that will be varied depending on the type of load of our system. Okay, and actually in the practical system most of our loads are actually inductive loads. Okay, and inductive load, in the inductive loads actually current lags voltage, right, by some angle. That angle is theta degree. That's why we can say that here the angle will, this armature current IA will be minus, because here in our system most of the loads are inductive loads. Okay, so how can we draw this line? So this is our VT. So with respect to this iron will be in theta degree lagging, right? Lagging means to go clockwise direction, right? So from this point we will go in the clockwise direction by the amount of pi, and we will get our iron. Okay. And let's say this arrow is denoting the magnitude of this. So now in the second step we have drawn this line, that is the armature current I. Now in step number 3 we want to decompose the phasor IA into G axis and Q axis components. Okay. So now we want to decompose this IA. Okay. Obviously this is a vector. We know that how a vector can be decomposed in their in two components, like in horizontal component and the vertical component, right? So for this IA, one component will be here in this side, like this, and another will be here. Okay, and this is the IT. Okay. So this is IQ. This is ID. Okay. Now using the formula, we can easily write the expression of ID and IQ with respect to this IA, right? What will be the formula? So you want to write IQ. What will be the IQ? With respect to IA, it will be the magnitude of IA this angle, the angle between IA and IQ is theta plus delta, right? Actually, here one point is missing. First we have to draw the E, okay? So this vector first we have to draw in the exact number. First draw the center in this progress E. So in step number 1 we drew this line VT, that is our reference line, and in respect to this we drew the armature current IA, and we know that the ideal difference will be the theta, and it will be I will be lagging with respect to this voltage, okay, as the most of the loads are like that, and the angle difference between this will be theta. Okay. Now in step number 3 we have to draw the generator induced voltage E, and we know that the vector will be delta. Okay. So this delta will be plus. Why it will be plus? I will say this thing later on. Step number 3, we have to draw this line, that is the E angle delta, because we know that this E is the generator induced voltage, right? And with this E, the associated angle is delta. We know this thing, right? So from our previous diagram, because we are discussing about the single machine inclining curve system, right? At the angle with inclining curve is 0 degree, but the angle with generator induced voltage is delta, right? So this is the thing that now we want to draw. So let's say we somehow know the value of delta. Okay, if we know the value of delta, then we can easily plot this line. Okay, and how actually we can draw, we can determine this delta. That thing will be discussed in the later part of today's discussion. Okay, but for the time being, let us think that you know this delta, and then this delta will be a positive value. Okay, so from this UT line, this is our reference. All of the phasors should be drawn from this reference line. Okay, so how can we draw this line? E angle delta. So from this VT, we have to go in the anti-clockwise direction, because here this delta means the leading angle, right? So here we are getting this E. This is the magnitude of this E. Okay, and this is the angle delta. Now in the fourth step, we want to decompose the phasor IA into IQ and IT. Okay, so here one point is important there. In the step 3, you view this line E. Okay, with an angle of delta, and whenever you are decomposing your IA, you can see the Q parameter of the Q component of this I is aligned with this E, right? So that thing is actually done for the mathematical convenience. Okay, actually to make our calculation easy in deriving the expression of P for cylindrical generator, we will assume that the direction of E and the Q axis. This Q means the Q axis and this D means the D axis. Okay, I think you should know this D axis and Q axis from this thing. Okay, so this is the D axis that is due to the current flowing from this rotor coil, and with respect to this D axis, our Q axis is orthogonal, right, to this D axis. That is 90 degrees difference in the anti-clockwise direction. So here, look, this is our D axis, okay, and this is Q axis. These are actually orthogonal to each other. And here also the IQ is 90 degree apart with the anti-clockwise direction from this I. Okay. So we have to assume that the Q axis and the E axis actually are aligned. Okay. So this is our one assumption. Okay. That's why whenever we will decompose the IA, we will get IQ exactly across the direction of the E. Okay, and we will get another component of IA, that is IP. Okay, so we have got these two components. Now we can easily write the formula of IQ and IP with respect to IA. Okay, now our IQ will be the magnitude of IA. Then the angle difference between IA and IQ is theta plus delta. Then will be simply cos theta plus delta. Okay. Then coming to the IP, it will be simply sine, right? Sine of this theta plus delta. Okay. These two are the components of IA. Okay. Any confusion after this? We have drawn this VT line, IA line, then E, then we decomposed the IA into IQ and IP. Okay. Now in the step number 5, we have to add the armature resistive term. Okay. That is the IA RA. Okay. So that is actually the voltage of armature resistive voltage term. Okay. So how can we draw the IA RA? It will be in the same direction of this IA. Why? Because let's say this is the armature resistive term, right? That is for the armature resistance. Let's say this is the armature resistance and this is the current armature current. Okay. And here let's say the armature resistive drop is VA. Okay. As there is only resistive component, we know that this VA and this IA will be in the same direction, right? Because for the resistive load or for the resistive component, there is no phase difference between the voltage and the current. Okay. Actually, the phase difference comes whenever the load is inductive load or the reactive load. So that's why whenever we plot this VA, this is actually this VA, we have to draw this line parallel to this IA. Okay. So let's say this is our IA, so multiplied by RA will be this much amount. Let's say this is the magnitude, and the direction will be parallel to this IA. Okay. Now this is our armature resistive drop VA, which is actually IARA. So we have added this thing with this VT, so VT plus IARA. Then in the next step we have to draw the JIT. Why? Because we know that along with this armature resistance we have some reactances as well, right? So let's say this is our reactance across the G axis XT and this is the reactance across the Q axis XT. Because we are studying the silicon machine, so for the silicon machine we have two different reactants. One is XT and another is XT, and obviously these two are not same. Okay, so that's why we have to draw this two reactive blocks separately. Okay, so the first one is the JITXT and the second one is the JIQXT. Okay, and as actually these are the reactive components, that's why we are getting some J here. J means the 90 degree phase difference. Okay, so whenever we will have the reactive component, we have to induce this angle with the J, right? Because we know that our impedance J means R plus Jx. So why is J? This is actually to represent this reactive part as an imaginary component, or actually to induce some 90 degree phase difference. Okay, that's why we are using this J in our expression of impedance. So whenever we will calculate the reactive drop, as well we have to introduce some J parameter, which will actually represent the 90 degree phase difference. So how can we plot this JXT ID? Because look, we already know the direction of ID, right? So this is our ID. This is ID. So JXT ID. So J means 90 degree. Okay. So how can we plot this 90 degree? Look, this ID. If we just replace it here, this is the direction of ID, right? So with respect to this, it's not it will be just in the leading side. Okay, this is the 90 degree. Now we can draw the JXT ID. Okay, so this is our JXT ID. Have you understood this thing? Any confusion here? So now we are at this point. After that, we have to draw the JIQXT. Okay, what is the direction of IQ? Here. Okay, so look, if we just place it here, this is our direction of IQ. Okay, with respect to this, J means 90 degree, like leading, right? So 90 degree leading means in the anti-clockwise direction, it will be 90 degree. Okay, now you can plot this JXT value, and it will be here. Okay, now you can see that what is actually the E. If you use the vector rules, you can easily say that our E will be equal to this Vt plus ILRN plus JXT ID plus JXT value, which is actually true, right? Because what is the Vt? Vt is our terminal voltage, okay, at the output side of the generator. Okay, so that will be the induced EMF minus all the drops. Okay, if we just place the drops in the right hand side, then it will be the drop plus this terminal voltage equal to this E, or the induced EMF. Okay, so have you understood this phasor diagram? Any confusion here?
So we know that G and Q axis are rotating. So does the rotation between the phasor diagram remain consistent due to the rotation?
Yeah, actually here, look, here all the components are like E, XT, XQ, like this. Okay, so actually all the parameters are the steady state parameters. So this diagram is for the steady state condition. Then in the later part of this discussion, we will see the transient phasor diagram. Okay, so this is actually the steady state phasor diagram, because you will see that this is E, not E prime, right? E prime is the transient. Also, you are getting the XT, not XT prime, right? So this is actually the steady state phasor diagram, and for the steady state phasor diagram, you can draw this thing. Actually, this diagram is drawn actually to derive the expression of P. Okay, our target is to derive the expression of P. Okay, from this. Okay.
Sir,
Yeah.
why do we draw the reference phasor that way? Why not? It's
Okay.
0 degree, right? Why
We are drawing it in the first step. We are drawing the reference phasor at an inclined angle. Okay, because we want to actually make this E lie horizontally. Okay, because whenever it will be in the horizontal direction, at that time all our calculations should be easier. Because look, here in this direction we have q axis with respect to this. This is the d axis. Okay. Then if we decompose this IA, we will get IQ and ID exactly in the vertical and the horizontal axis. Okay. At that time our calculation will be easier. Okay. That's why actually we are plotting it in this direction. Okay. This is actually in our hand. We can plot it like here or here. This utility doesn't mean that we have to plot it always in the horizontal direction. It is up to us actually in which direction we want to plot it. Okay.
Sir, how would we know if IQ and ID are like properly horizontal and vertical? Like those values can.
Yeah, exactly. Because this delta will be known to you. Okay. We haven't yet derived the formula of delta. So whenever we will see the formula of delta, you will see that here all the parameters actually are known to you. Because all the parameters will be given in the problem. Okay. So from that parameters you can easily determine the delta. So if you know the delta, then you can easily maintain this distance. In which direction will be Vt and which will be E.
Sir, I mean, is it always going to be like perfectly horizontal and perfectly vertical, like with Q axis and D axis? When we draw the figures, like in this
Yeah.
figures.
So actually, if this is not perfectly horizontal, then actually I think it will not make any problem, because if it is like this, okay, then with respect to this, your height will be like this, okay. But always there will be 90-degree difference between this d axis and d axis. This is must, okay. And also these angles should be maintained. Like your angle difference between VT and IA should be theta. Then angle difference between VT and E should be delta. Then angle difference between this IA and E should be theta plus delta. This should be maintained. Must. But this direction is not like this, so actually make our calculations easier. Okay. Now actually from this phasor diagram, now we have to make some assumptions. Okay. Our first assumption is that our armature resistance, this parameter is very much low in magnitude, okay? Because we know that for this RA we get some copper loss, right? Or the I square copper loss, and we want to minimize the loss. That means for the manufacturer, it is wise to build the conductor as a way that the conductor reactance remains as much low as possible, right? That's why we can easily assume this thing that our RA, this is very much less with respect to this H, the reactance. Okay. In that case, we can neglect the armature resistance drop. So now our armature resistance drop can be assumed as 0. So if it is 0, you can see what is the difference of this diagram and the previous diagram. There is no this reactive resistive drop component, right? So this thing has been eliminated. That's why this thing has been shifted here. And this is like this. Okay. Now can you see this? Okay. This is good. This is JXDID and this is JXQID. Okay. Now what will be the E? Now E will be simply VT plus JXDID plus JXQID. Okay. It will be simply the E. Now, from this diagram, we want to actually formulate some expression. The first expression is that the magnitude of E. Okay. So you can also write this magnitude of E in this way, that it is actually the VQ. Okay. So before that, we haven't discussed the VQ and the VD, right? So we have the VT. Similarly, as our IA, we can decompose this VT into two components, right? One will be VD, another will be VQ. Okay. So in this axis we will have the VD, and in this axis we will have the VQ, because we know that this is the Q axis and this is our D axis, right? So this is our VQ and this is the VD. So once we can decompose these two, now we can write the expression of the magnitude of this E. Okay. What will be the magnitude of E? It will be simply, let's say this VQ plus this much amount, right? This is actually nothing but JXDI, right? Everyone understood this thing? The magnitude of E, that is from here to here, it will be simply VQ plus xdx, right? So what is our VQ? VQ means the VT. Look, VT cos delta, right? Because here the angle difference is delta. So VQ will be VT cos delta and VT will be VT sin delta, right? Now what will be the magnitude of E prime? E, it will be simply this VQ. VQ means what? This VT cos delta, the magnitude of VT then cos delta, because we are actually considering the magnitude here. That's why the magnitude of VT cos delta. This is actually nothing but the VQ, right? Plus this amount. What is this amount? This HDI, right? In magnitude, it is actually HDI. Okay, so whenever we will consider the magnitude, we do not need to place this J. Okay, so it will be simply HDI. Now, from this, if you just take this portion in the left hand side, it will be the magnitude of VT cos delta, then it will be here. It will be E minus HDI. Okay, so this is the equation has been got from the previous equation. Okay. Now, what is this? This is actually the VQ, right? Because this is VT cos delta. So VQ equals to E minus HDI. Okay. Then from this equation we can write the expression of ID. What will be the ID here? Look, it will be E minus VQ divided by X. Okay. Actually, from this equation, if you just take ID in the left hand side, so in the right hand side you will get the E minus V2 divided by X. Okay, so this will be the expression of our ID. What is the ID? The t-axis component of ID. Okay, previously actually we saw the formula of ID like this. So ID was IA then sin theta plus delta, right? Previously it was like this because here the angle is theta plus delta. So IQ is IA cos theta plus delta and ID is IA sin theta plus delta, right? But here we have seen another expression, that is the ID is E minus VQ divided by X. Both are actually same. So that is the ID, that is E minus VQ. V2 is VT cos delta divided by X. Okay. Then what will be the VD? VD is simply, look, this is the VD, this amount, right? This and this actually are the same, right? So VD in magnitude will be equal to XT value. VD means XT value. So what will be the IQ? It will be VD divided by XT. So this is our IQ. What is VD? VD is the component of this VD, that is the VT sin delta. That's why we have written here VT sin delta divided by XT. Okay. So we have actually derived lots of equations here because after discussing this, we will solve some numerical problems. Okay, in that problem we will see that sometimes few parameters are known. With respect to that few parameters, we have to calculate the other parameters. Okay, so that's why you have to know all the relationships. Otherwise, it will be difficult for us. Okay, let's say you do not know the value of I. Okay, so at the time, how you can determine the ID? Okay, so if you know this thing and if these values are known to you, then actually you can find the value of ID. Okay. So that's why from this phasor diagram you have to know all the relationships. At that time you will be able to solve the numerical problems. Okay.
So, you explain again this last one.
These two.
Yeah, sorry.
This line.
This last one. Alright.
This line and this line, right? So here, how can we write this line? This is the VQ. Okay.
30%
This is simply the VQ, right? This is VQ. VQ equals to E minus AC, right? E minus HDID. This equation we have got from the previous equation. No? This is the E. Magnitude of E will be simply this VQ plus HDID, right? That thing has been written over here. What is VQ? Instead of writing VQ, we have written here the VT cos delta, the same thing. Okay. Then here we have taken this thing at one side and other two at the other side. So it will be simply VT cos delta equals to E minus HDI. Then from here, this is simply the VQ. Okay. So VQ equals to E minus HDI. Now what will be the ID? ID will be simply E minus VQ divided by X. From this equation you will get this thing. If you just write some few lines, then finally you will get this ID that is equal to E minus V2 divided by X2. Okay. Then what is the VD? VD is this amount. Okay. This amount and this amount actually are the same, right? Let's look. This line actually the same line, right? So this and this are actually the same. So what will be the VD? VD will be X cube I2. Then from this expression we can write I2. I2 is VD divided by X cube. Okay. So I2 is VD. What is VD? VD sin delta divided by X cube. Okay. So now in the next slide we will see that we will actually now formulate the expression of PE. Okay. So what is actually the PE? Look, the PE is the real part of VT multiplied by the conjugate of IA, right? Because in the last class maybe we saw this equation, right? Because we have the complex power S. Okay, let's say this is the power triangle. This is the power triangle getter. This is the complex power S. This is the real power P. And this is the reactive power, right? And we actually wrote that our S will be P plus J. That is the P is the real part of the complex power S and Q is the imaginary part of our complex power S. Okay. And for this S we can write S will be V multiplied by the conjugate of current I. Okay. Then what will be the P? P will be simply the real part of this. The real of V multiplied by the conjugate of I. Okay. That's why you can write this. What is our PE? P will be the real part of this VT and multiplied by the conjugate of I. Okay. Then actually what is VT? Look, we have already decomposed the VT into VQ and the VT, right? So now we can write like this. What will be the VT will be VT plus JVQ. Okay. So actually for this phasor diagram there are few assumptions that you have to actually make. Okay. I am actually writing these assumptions in the board so that it can be easier for you to follow the slide. Okay. The first assumption that actually we made in the first slide here of our today's discussion, that was the E direction of E and Q axis will be same. Now our second assumption is that P axis represents real axis and Q axis represents imaginary axis. This is actually the convention. Okay. Now we will use this assumption here. So our D axis component will be the real component and the Q axis component will be the imaginary component. Okay. That's why what will be the VT? How can we write this VT? It will be simply the real component, that is VT plus J, the imaginary component VT. Okay. So it will be VT plus JVT. Okay. Then similarly IA, what will be IA? IA will be the real component, that is the ID plus the imaginary component IQ or JIQ. Okay. Now we can place these two formula into this expression of PE. That will be the PE will be the real part of VT. What is VT? VT plus JVQ. Okay. And the conjugate of IA. What is IA? ID plus JIQ. So what will be the conjugate part? Simply before the imaginary part the sign will be changed, right? So then it is plus, it will be minus if you do the conjugate of I. Okay. Do you know this thing? So this is the VT multiplied by the conjugate of I. Now look, we have separated the real part and the imaginary part from the expression. Just multiply these two. Okay. Then these two will be the real part. We have separated this real part, and this will be our imaginary part with this z term, right? Then we want the real part, right? So that's why this has been excluded, and we have only this part, that is the VD ID plus DQ ID. Okay. Then finally, you know the expression of VD ID, DQ ID. So in the previous slide, we have found the VD, DQ, then ID, IQ. If you place all the values here, then after some few lines, you will get the final expression of P. Okay. So this is our final expression of P. I am not showing the intermediate lines that are showing here. Okay. You can do it by yourself. Okay. But finally, we are getting this P. Okay. So this P is for the salient generator. Okay. Can you remember the P expression for the non-salient pole machine? What was the P? P was the magnitude of P in P sin delta divided by x1, right? This was the expression of P for non-salient pole machine, and this is the expression of salient pole machine. Okay. This first term is same as the expression of P for non-salient pole machine, right? So this first term is actually the same. And for salient pole machine, there is one additional term, this term. Okay. And this term is called the reluctance power. Okay. What this is called reluctance power? Where you can see that the difference between the T-axis reactance and the Q-axis reactance. Why these two reactants are not same? Because the reluctance were different, right? In this slide, we saw that the air gap actually is different. That's why the permeance across T-axis is higher and reluctance across the T-axis is less, right? So the reluctance of T-axis and the Q-axis are actually different, right? That's why due to the difference of reluctance in T-axis and Q-axis, this is called the reluctance power. Okay? So this is actually the reluctance power, this additional term. And for the non-salient pole machine, this xg and xq actually are same, right? For the non-salient pole machine, xg and xq are actually same. At that time, this will be 0. So this whole term will be cancelled. Then we will get only this first term. Here you can see this power, we have got this due to the difference of the reluctance across the T-axis and the Q-axis. That's why we are getting the difference of reactance, that is xg and xq, right? That's why it is called the reluctance power. This term is the reluctance power. Only this term. Okay. So if in the question paper it is asked that determine the reluctance power, then you have to find only this portion, not the full expression of P. Okay. Because within this P, only this term is called the reluctance power. And if we add this term, then we will get the complete P for salient pole machine. Okay. Now, in the next slide, now in this step 3, I said that how can we determine this delta, that things will be discussed in the later part of our discussion. Now we will focus how can we determine this delta parameter. Okay. So now the expression of delta for the salient pole generator. Okay. So this is the discussed here. Okay. We have neglected the armature resistive drop. That's why there is no armature drop here. Okay, IARA. Now from this we can write some expression like this. What will be the magnitude of T? It will simply this VQ plus XDID, right? What is VQ? VQ is the VT cos delta plus XDID. Then this ID is, what is ID? The magnitude of IA sine, this is ID, sorry, this is ID. Okay, so what will be the ID? The magnitude of IA sine theta plus delta, right? That thing is written over here. Okay, so we have just replaced the ID with this. Any confusion? Then we know that what is the VD? This is the VD, this and this will be the same, right? XQI. Now, what is VD? VD is actually the magnitude of VT, then sine delta, right? Because VQ is magnitude of VT cos delta Okay, then it will be simply x cube is remain here. But what is the expression of I cube? I cube is the magnitude of Ia cosine of delta plus theta, right? So this is this. Now look, we know the cos A plus B formula, right? What is the formula? Is actually the cos A cos B minus sin A sin B, right? So this formula has been written here. Cos delta plus theta. So this cos delta cos theta minus sin delta sin theta. Now this thing, look here, this minus this will be multiplied by this, right? So we will get x cube Ia cos delta cos theta minus x cube Ia sin delta sin theta, right? Then if we take the sin delta sin theta part in the left hand side, we can take the sin delta common from this term and this term, right? Then it will be simply dt plus x cube Ia sin theta multiplied by sin delta, okay? And this term will be in this side, x cube Ia cos delta cos theta. Can you follow? How can we actually get this equation from the previous equation? I am writing it in the code. Okay. So in the left side it is actually the dt sin delta, right? And in the right side, this term x cube I cube will be multiplied by this 2, right? So it will be x cube I cube cos delta cos theta minus x cube I cube sin delta sin theta, right? Now take this term in the left hand side, right? So it will be simply, let's say I am taking this term here, x cube I cube sin delta sin theta, right? Now this term has been shifted to the left hand side with a plus sign. So from this 2 you can common this sin delta, right? It will be sin delta dt plus x cube I cube sin theta, right? And in the right hand side it is actually x cube I cube cos delta cos theta. Okay. Now take this part in the right side. Okay. And this cos delta, if you take it here, it will be the sin delta divided by cos delta, right? And this is actually nothing but the tan delta, right? So tan delta will be, take this part this side, so it will be x cube I cube divided by this thing pt plus x cube I cube sin theta. Okay. So look, this thing tan delta is yeah. So this is the Ia, right? Also there is one cos theta here. So the cos theta divided by, so x cube Ia cos theta divided by bt plus x cube Ia sin theta. Okay, it will be like this. Then delta will be tan inverse of this term. Okay. Now look, can we determine the delta from this expression? Yes, because all the parameters is known to us. Let's say what is x cube? The reactance across the q axis. So this thing will be given in the question paper. Okay. And what is the Ia? So I is the armature current. Okay. So you can somehow find this Ia because the real power information and the voltage information will be given in the question paper. So from that, and also the complex power will be given. Okay. So from this type of expression you can find the expression of Ia or the level of Ia. Okay. In the next class we will solve some problems. In those problems you will see that if you have this P, V and this S complex power, you can find the Ia easily. Okay. So this Ia is known to us. What is this? Cos theta, theta is the power factor angle, right? So this power factor value will be given in the question. Let's say power factor is 0.8. What will be the power factor angle? It will be simply theta will be cos inverse of 0.8, right? So from that value, from that expression, you can find the theta. So cos theta is known to you. Similarly, sin theta you can find, right? Then VT is the terminal voltage. This value will be given. Okay. In the next class, no problem. We will solve on. At that time, this thing will be clear to you. Then XQ again, this thing is known to you. Then I here, so you can into it previously. Okay. So that means you can easily calculate the value of delta at the beginning of your solution. Okay. So whenever one problem is given, so maybe within some few steps you can successfully determine the value of delta. Okay. So it is not a big deal to find the value of delta. Once you will find the value of delta, you can easily draw a physical diagram because at that time this E should be in the horizontal line and with respect to this is our reference point, that is the V. Okay. Now any question?
Sir, I'm sure E plot.
First you will plot this reference point. This is the step, right? You can do that one, no problem. Okay, because you know that, yeah, with this specific reference point, output will be in the horizontal line, right? So you can draw it fast, then you can draw it forward. Or if you draw it, then you draw this thing. This is the same. Okay. Now here, look, the same discussion but for the transient case. Okay. So now we discuss for the mysterious case. Okay, here look, here all the parameters are actually the steady state parameters. Okay. Now this same value diagram is replaced here with the transient parameters. Look, here it is the prime side, right, or the bar. That is EQ bar, EQ prime. There is XD prime, right? But there is no XQ prime here. Okay. So there should be some XQ prime here. So why it is not here? Because for the transient state, this XQ and XQ prime are actually same. Okay. So why this is same? That is actually our assumption number 3. Okay. So that I want to write here. Because you know that whenever we discuss this slide, so this D axis was due to the current flowing across the rotor coil HDLT line, right? But the Q axis we just drew it with respect to this Q axis, but there is no rotor coil associated with this Q axis, right? So if there is no rotor coil, so we will not get any magnetic energy. Okay, because there is no current or no rotor coil associated with this X axis. So that means actually across this axis we will not get any magnetic energy. So if there is no magnetic energy, so in the steady state, in the transient state, both things will be same. So there will be no substantial change in XQ value in the transient. So that's why we can assume that our XQ actually is equal to the XQ prime. Okay, that's why here in the transient saliency case, the E is replaced by EQ prime. Why EQ prime? Because this is across the Q axis. That's why it is written the EQ prime. We can write also E prime. It's the same thing. Then this XD is replaced with the XD prime. Okay, and this XQ is simply the XQ because we know that in the transient state it is XQ prime and steady state XQ are actually the same. Okay. Now for this diagram there are few things that you can actually derive. This is the same expression. Okay. This was your P, right? Now if you want to write the P expression for transient case, you will just press here, you will just write it P prime, then sin Vt sin delta divided by xd prime. Okay. Then Vt square xd prime minus x cube divided by 2 xd prime x cube sine 2 delta like this. So this thing has been written here. Look. EQ prime Vt is Vt here. Xt is replaced by Xt prime. Here also Xt is replaced by Xt prime. Here also. But Xt is kept same as it is. Okay. Now the same thing, you can write the expression of the magnitude of EQ prime. Okay, that will be this VQ plus this xt prime ID. What is VQ? VQ is the Vt cos delta. Okay, then actually from this thing you can write, look, this is the, what is ID? ID is the magnitude of Ia sine delta plus theta. This thing, then from this thing you can write, look, what is ID? ID is the Ia sine delta plus theta. Then actually look here from this thing, this part is, if you take this thing here, so EQ minus Vt cos delta divided by this thing, like this. Okay, so you will get the ID, that is the Ia sine delta plus theta, which will be simply E minus Vt cos delta divided by x. Okay, then what will be the EQ prime? EQ prime will be, look, this plus xt prime. Now this portion has been replaced by this term. It is again E minus Vt cos delta divided by xt. Okay, that are actually the steady state parameters. Okay, here it is the transient E prime, but here this is the steady state E. Okay, also this is the steady state value of xt. This is the transient state of xt. Okay, so if you know the steady state value of E, you can easily find the transient value of E using this expression. That is the thing that is derived. Okay, so in today's class we have seen lots of expression here. Okay, so but actually the most important thing is that you have to remember this schedule diagram. Okay, if you can remember and plot this schedule diagram in the exam hall, then you can easily derive this expression by your own. Okay, so there is nothing to actually memorize. And in the next class, I will try to solve some numerical problems. At that time, all of the things will be clear. Okay. Why is this? Actually, this E is along the EQ axis, right? That's why you have written the EQ prime. You can write it